Hello everyone, welcome to another video of GPU programming with Mojo. Today we shall quickly recap some of the key GPU concepts and implement two simple GPU algorithms. The first concept to keep in mind is layout tensor, which is an abstraction provided by Mojo to safely and correctly access a memory location. Second is boundary condition, which is to activate threads which are needed and prevent other threads from doing so. Shared memory is a memory visible to all the threads in a block. It is in close proximity to the block, hence the read and write operations are at least 20 to 30 times faster than global memory. So when possible, we have to use it. Keep in mind that the shared memory doesn't have any data initialized, so we have to copy the data from global memory onto the shared memory. So the question we have to ask, is the copy worth it? Fourth, closely associated with shared memory is barrier, which has to be called appropriately to ensure the threads are in sync and no misbehaving among them happens. So keeping these four concepts in mind, you can sort of design a blueprint for all the GPU algorithms. You would start off creating a shared space or a shared memory. You would enforce a boundary condition, meaning you would activate certain threads that you want to start off. Then you would call a barrier function appropriately so as to ensure the threads are in sync. Finally, you would perform an operation, meaning if it's a pooling operation, you would perform that. If it is a convolution, you would perform it. So essentially, the actual implementation of the algorithm comes in the latter half of the algorithm. The first three steps or the first few steps are ensuring we set up the algorithm with the right memory locations and threads. So let's go into the implementation. We'll import all the necessary libraries along with initializing threads and blocks. To keep matters simple, we'll consider one block and 8 threads. So the first kernel we're trying to implement is the pooling operation. The pooling is an operation that is defined as a summary or a reduction operation using the max or sum or average functions over its neighboring elements. To keep the scope very narrow for this video, we shall only consider summing the elements of the last 3 locations. So with that in mind, let's see how the kernel is implemented. Again, when we go through the code, keep the blueprint in mind. Step 1, create a shared memory. Closely associated with the step 1 is always get the global and local index of the thread. Then perform the copy operation from the global memory onto shared memory. Call the barrier function whenever you do that so as to ensure the threads are synchronized. Finally, this is where you would think and design the algorithm. In a GPU world, you would write a for loop and simply sum up the 3 locations accordingly and then finally compute the result. But keep in mind, you have to traverse the entire size of the vector in order to do so. But here, GPU, you have the mindset is you have to do it in parallel, meaning you have to use as many threads as possible to perform the parallel operation. So hence the same result has to be achieved by doing things that can be broken down and done in parallel. So in order to do that, first let's look at it visually how it's done, then the code might make more sense. So in the GitHub, I have provided a HTML web page, which is an interactive tutorial to explain the code. To start this, you would just right click and say show preview. If you're using Visual Studio Code, there is an extension called live preview, which you can use to spin up a quick web server to host the HTML page. And the good thing about it, it puts it right next to the code, so you can run both of them in tandem. I'll adjust the video here, the window here. So let's look at the steps. So I'll go to pooling, and then first step is copy from global to shared memory. And then if you, the algorithm goes like this. So thread 0 is instructed to just copy its element to the output vector. Why? We said the last 3 locations. It doesn't have the last 3 locations. It just has one location. So as is, copy it to the output vector. Thread 2 has one operation to perform, which is add 2 plus 1 and store it in output vector. So it doesn't have last 3, but it has just last 2, which is the location that it's currently hosting plus the one before. The actual algorithm or the scope of the algorithm starts from thread 2 when it has 3 elements and it has to add those consecutive elements and store them in the resultant output vector. Now keep in mind, thread 1, 2, 3, 0, all of them are acting in parallel. So all 4 threads in this case are computing the last 3 elements and writing it to the output vector simultaneously. And that's the difference between a CPU where you would traverse in a for loop one by one sequentially and do it. You will do it quickly nevertheless, but you still have to traverse it to the size of the vector. Whereas here, 4 threads acting simultaneously and computing 4 operations at the same time. So of course, in this case, there are 8 elements, so all 8 threads would do the same. So thread 4 would do 3 plus 4 plus 1 and so on and so forth. So that's how the pooling operation is done, where the output is computed by 8 threads and writing it to the 8 locations in the output vector. So you'll see the same thing where we handle the first 2 special cases. And then from the third case, where essentially this is saying from thread 2, 3, 4, 5, 6, 7. So 0 and 1 not included. From 2 to 7, ensure that you compute the sum for the last 3 locations. You would then call the kernel to produce the desired output. Next is the dot product. So the dot product is defined as element-wise multiplication of 2 vectors and then sum those to get the final answer. So in this case, 0 into 0, 1 into 1, 2 into 2, and then sum them up to get the answer, which is equal to 5. So following the same blueprint, we first create the shared memory, then we get the global index and the local index of the thread. We copy it over, but here instead of blindly just copying it over, we can actually finish the multiplication. So it's multiplication of 2 vectors, then compute the sum. But since while copying you can actually do this multiplication, you would actually perform that operation and then copy it over to the shared one, which is a convenient way of doing one operation and getting rid of it so as to make our algorithm easier further. Finally, we do what's called as parallel reduction. Again, to understand this operation, let's quickly jump over to the interactive web page. Choose product. So step 1 would be to copy, but instead of blindly copying it, we multiply and then copy it over. We sync it through the barrier function. And now the parallel reduction says that divide the vector by half and only consider the first half and activate only the threads in the first half and ensure that they access their location plus the size, half the size of the vector. So what I mean by that is ensure that you only activate threads 0, 1, 2, 3. Okay. And then we instruct thread 3 to first access its element, which is in this case 4. And then we say ask it to jump 4 locations and then compute the sum of 4 and 2 and store it in its corresponding location. So that's a 6. We give the same instruction to 2, which is access its location, which is 6, jump 4, access this, so 6 plus 2 is 8, compute the sum and store it in its own location, which is 8. So this is called parallel reduction. So you're doing things in parallel, you're reducing the size of the vector from 8 to 4, and now you'll see in the next loop, it will be from 4 to 2 and 2 to 1. So this is a very popular algorithm in GPU's world, where any reduction or compute or any sum computation involves such reduction in vector size, and then only involving half the number of threads to do the operation. Now you will see that 4 became 2, and now you will see that since the 4 has become 2, you would instruct threads 1 to access its location, which is 2, and then add 6 to it, so jump 2 locations. So since the stride or the vector that we are trying to consider is only half of 4, which is 2, we say access your location, jump 2 locations, which is 6, and compute the sum and store it. So 2 plus 6 is 8. 2 plus 6 is 8. 6 plus 8 is 14. So the trend is reduce 8 by 8 into half, which is 4, jump 4 locations, reduce 4 to 2 and jump 2 locations, reduce 2 to 1 and jump 1 location. So reduce to 4, jump 4 locations, reduce to 2, jump 2 locations, reduce to 1, jump 1 location. So that's the trend of the algorithm design. And once you do that, the final answer is stored in the first location, or which is accessible by thread 0. Hence, we then copy that over to our output vector and print the sum. So now if you look at the, so we say that first we divide total threads per block, which is 8, divide by 2, which is 4. We call it a stride. Then in the first pass, consider only 0, 1, 2, 3, and then take the shared location, add them to the shared location itself, but then also access 4 strides, which is 4 strides apart. Once you finish the first loop, now reduce your stride by 2 and then repeat the same until you run out of all the strides that you can perform. Finally, the thread 0 will have the final answer. Copy that over to the output vector and print the sum. You will see that the sum of elements is 140 here, because we initialized it to from 0 to 7 for both the vectors. So hopefully that gave you a sneak preview into the world of GPU algorithms as to how they are designed. Hopefully it gave you a sense of blueprint as to how to design such algorithms. So in all the future further videos, we will look into some sophisticated ones and then see how we can apply the same principles and implement them. Thank you.